Right. Hey,
Hey guys.
University. What did I do that? About this goal. Dr. Trepp, is there always hydrostatic pressure inside the valve? Like,
If there's a fluid inside, yep.
there's a fluid inside. Okay.
Yep.
So then that coefficient would have to be entered into the software, or it would know based on what it happens, or
Well, what do you mean coefficient?
well, I mean like the number, so the pressure comes out.
Uh-huh.
It's one of the constraints that you put in,
Yep.
and then it'll give you the simulation, right?
Yeah. So you would put so for the finite element class, so normally that pressure would be computed based on whatever fluid's in there. And so it's based on the density of the fluid, right? And how deep it goes.
Yeah.
But since I'm only giving you just a segment of the pipe, you can just manually put in a pressure on there. Yeah. And so you can choose that pressure based on, because if the fluid is moving too, then there's going to be additional pressure because of that, because the fluid has to be pressurized in order to push it through the pipe too. So yeah, so you have freedom to choose what pressure you want to put in. Yep.
So I'm doing the wall break analysis class.
Yep.
I did a simulation, but did not exceed the stress, did not exceed the yield strength, but the deformation was like a meter. So
Oh,
I'm assuming that it could be that the bar could just bend without it breaking apart. Is that a
1 meter is pretty
situation?
big though, because
Yeah, it's even giving an error warning saying deformation error or something.
yeah, 1 meter usually, because it's not that big of a wall bracket, is it? It's
No.
Is it fixed properly? Like you have a
Yeah,
fixed?
I
Okay.
actually run that. I ran it twice.
Uh-huh.
Well, I was adding the force a lot to try to reach the max or the yield strength.
Okay. Uh-huh.
And after a while, it exceeded the deformation. I started
Okay.
getting the error.
I see. Send me screenshots because one meter is pretty big to
Yeah,
I'd like to see it just to see.
because I do have like the 3 mounting holes as a fixed position.
Okay, that
And
makes
the
sense.
load is on that individual hole on the side.
Got it. Okay.
The down force.
Okay. Yeah, that sounds reasonable. Yeah, send me screenshots and let me take a look.
Okay.
Yeah.
But wouldn't the fixed surface be a phase on the part?
I did it for the wall though, because obviously when you tighten the screws, it will like kind of like a strong static
Yeah.
friction. So I assume like for one of the scenarios I put that as a fix.
Oh, okay. I see.
On this one, I'm doing it on the ceiling. So
Ah,
it's getting pulled down, it's only the mounting holes getting all the stress.
You guys are working on different projects. So 540 has two geometries, and then 410
okay.
has
Oh,
a little bit simpler geometries. Yeah. It's not 58 degrees right now. Okay, there we go. 84.
Where are week 10 lecture to?
Wait a second.
Where are week 10 lecture to?
Yes.
Thank you.
Yep. Mhm. All right, it's 4 o'clock, so let's go ahead and get started. Good afternoon, everyone. How's everyone doing today? Good, good. All right, and so you know, probably first thing you're noticing today is that we have a different starting screen. And so I finished writing up the specifications for the final project just this morning. And so I wanted to discuss that with you, just so that you can kind of, you know, at least start thinking about what topic you want to do, and start forming your groups if you want to work in groups. And then, you know, start doing some of the research. So I'm still writing up the rubrics. And so, you know, I'll get those out to you as soon as I finish it, but I at least want to give you, you know, I want to let you know what I expect you guys to do for the final project, when it's due, what the topics are, so that you can kind of start thinking about these things now, because it's, you know, we've reached week 10, and this is when this is usually when I like to assign final projects, so that, you know, you guys have enough time to work on it. Okay. All right. And so the whole idea with the final project for this class is to have you guys do kind of a bigger research project. Okay. And so for a lot of the homeworks that I've assigned so far, you know, I've let you guys do you know, research into specific topics in biomechanics. Because the thing with biomechanics, you know, as kind of we've said a lot in this class, is that it's a very wide topic area. And so there's so many different areas of biomechanics that, you know, so many really interesting areas that we're just not going to be able to get to in this class, just because you know, this is kind of the only one of its kind right now in our college. And you know, we kind of have to build up a lot of things from scratch. But I know just from talking to you guys throughout the semester, and, you know, from a lot of your introduction emails at the beginning, that you guys have a lot of really strong interest in a lot of the, you know, interesting application areas of biomechanics. And so, you know, I want to give you guys a chance to explore those areas, to give you a chance to research them. And first of all, get credit for it, right? I think it's one thing to, you know, be interested in a subject, but, you know, when you're constrained with so many other, you know, responsibilities in your class or your jobs, you know, it's hard to kind of find the time for that. And so, you know, I wanted to make a project where, you know, it'll fit the requirements for the class, and so you'll get credit for it, but you'll get to explore something that you're really interested in. Okay. But, you know, I want you guys to approach this from the perspective of, you know, I want you to be thinking about, you know, taking what you're learning about your specific area of interest and then teaching it to the class, okay? And so, a big part of this project is going to be a final presentation that you or your group are going to put together for the last week of class. And think of that as kind of like a small lesson that you're going to give, to teach the class about, what you've researched about this topic. Okay? Because you'll see from the bottom there's a lot of, really interesting topics that, I've spent a long time, thinking of these, but, you might come up with something different as well. Okay. All right. And so the due date for the project is the Monday, December 20th. Okay. And so that's a little bit less than 2 months from now. And so this is the absolute last day I can make the project due. And so, once we get closer to that date, I know always a few people ask me if I can extend it, but that's the absolute last day I can have it, because, I have to have all the grades in before Christmas. They actually gave me a couple of days after Christmas, but I normally like to see my family for Christmas, and so I don't want to spend that time grading. And so this is kind of the absolute last day I can have it due and still have time to grade everything, because I have your guys' class. I have 3 other classes at final project as well. And so, I'm making all the final projects due on the same day. Okay. All right. And so, a big part of this project is going to be the research that you do. And so, you can kind of get started on that now. And then once you're done with that, you're going to basically write a report and make a presentation. Okay. All right. And so for the rest of the, what I had planned is that I'm going to go through the specifications with you guys. And so you can find this document on the Canvas site. And so if you go to our files, our file folder on our Canvas site, and you go into the folder called projects, right, or project, then the only document in there is the specifications for this final project. Okay. And so that's the document that I'm reading now. And then you can find it on your own. Okay. Groups. Oh yes, groups. Let me mention that before we go. So, and so I'm going to be pretty flexible with this. And so you can work in a group, or you can do it solo if you want. Then I'm totally fine with that too. But the maximum amount of people that you can have in your group is 3. Okay. And I don't want to go beyond that. And so, if you have 4 people that want to work on a project, I'm going to ask you guys to split up into two groups of 2. Okay. But you can either work with 1 person, 2 people, or groups of 3, and all of that is fine for me. Okay. Any questions on this so far? Okay. All right. So let's talk about the project requirements. Okay. And so there's kind of 3 main areas, or I would say 4 main areas, that are going to be required for the project. Okay. And so the first is going to be, just the introduction, background information, and significance. Okay. And so I've kind of grouped all of these together because they all kind of naturally go together. And so, everyone's going to be studying a very, if you look at the topic list below, and we'll go over that later, that there's a very wide variety of topics that you can do for this project. And so, a big part of the requirements is kind of introducing the project or introducing your topic to the class, and giving a good description of what it actually is. Okay. And most importantly, describing why it's important. Okay. And so this last part is kind of key right there. Okay. And so, think about when you come to a lecture, right? It'll be for this class, for another class, right? At least for me, the best lectures that I always go to are the ones where, the instructor or the professor makes me feel like what they're teaching or what they're telling you is important to them, right? And so I want you to really think about, how can you describe your topic, and how can you make it so that, that you can explain why it's important to study in terms of biomechanics. Okay. And the other characteristic of your introduction is that, it should place it within the context of this class. Okay. Right. And so a lot of that might be obvious, kind of just based on the topics that that you'll have available. But you should put it within the context of, of the specific things that we've discussed in this class. So, does it have to do a lot more with, tissue biomechanics? Does it have to do more with static analysis? Does it have to do more with dynamics, which is kind of what we're going to start today? Okay. And so, really kind of refer to those topics and really dive deep into, how your specific, application fits into those areas of the class. Okay. All right. And, of course, during in your introduction, feel free to use as many figures or as many pictures or as many examples as you can to kind of, get your point across. Okay. All right. And so the second section here, this is going to be the meat of your project, and that's going to be biomechanical analysis. Okay. And so I wanted this project to be more than just like a book report. And so I don't want you guys to just go through the literature or look through some articles and just summarize them for me. And so I want you guys to actually apply some of the methods that we've learned in this class. And so things like static analysis, and we'll go over dynamic analysis here. Okay. To actually analyze some of those examples that you're taking a look at. Okay. And so I'll give you an example. And so one of the topics that I have at the bottom is animal locomotion. Okay. And so in that topic, I want you to analyze, how do animals actually move around? How do they stand, and stuff like that. Okay. And so if you chose that topic, then part of your project is I want you to actually do some calculations, right? Do some static analysis calculations, compute muscle forces, compute joint reaction forces, for like a cat, right? And so let's say that you're interested in studying how a cat moves. Okay. So I expect to see some calculations like that in your report. Okay. And of course, just like we have been doing in the lectures, you're probably gonna have to make some assumptions, and you're gonna have to simplify some geometries. Okay. And so if you look at all the examples we've done so far over the last few weeks, most of the times we assume that the body's like a stick, right? And so that's perfectly fine too. Okay. And so, if you're having trouble coming up with certain problems that you're going to do for this project, look at some of our examples in class, and look at how I've simplified geometries and made it easier to do the computations. Okay. And so in total, for your final report, you should have at least 5 of these analysis types. Okay. And so if you do, say, all static analysis, you should have 5 static situations that you're going to analyze, 5 free body diagrams. Okay. And at least 2 of these should make it into your final presentation. Okay. And so think of these as kind of like worked example problems that you would do as part of a normal class. Okay. And so I want you guys to be coming up with those example problems, doing the calculations, and kind of setting the stage for all those things. All right, so after you've done with the biomechanical analysis, then we go on to the discussion. Okay. And so this is usually the part of a scientific paper where you take the data that you've obtained, either through an experiment or through your calculations, and then start to make some conclusions about it. Okay. And so for every topic, there's going to be some discussion questions that you can answer, right? And so, questions about, what is the cutting edge of the technology for this right now, or what are the specific advantages of this specific device? Okay. And so it was hard to kind of be specific on this because all the topics are so different. But basically, there's specific questions about each of the topics that make them interesting to study from a biomechanical perspective. Okay. And so what I want you to do in this section is to take the results from your previous section. Okay. So take the results from your 5 biomechanical analyses and use them to explain, why your topic is so interesting. Right. And so going back to the example of the animal locomotion, right? So let's say that you did an analysis of, a cat jumping up on a chair, right? And you computed like the muscle forces and the joint reaction forces within the cat. Okay. And so what are those muscle forces? What does that say about how a cat is designed, right? And so what is it about a cat's body that makes it optimal for performing these actions? Okay. So those are the kinds of questions I want you guys to think about and answer in your discussion section. Okay. And so every topic's really different. And so it was kind of hard to be kind of, more specific in this section, but, I think once you start exploring your topics and really researching what are the interesting scientific questions, then, those will become a lot more clear. And of course, you can talk to me about these as well. Okay. All right. And so the last requirement is not something that you're explicitly going to write in your report a lot, is the sources that you're going to use. Okay. And so altogether, your group needs to have at least 10 different sources that you're going to use to put together the information for your project. Okay. 3 of these sources need to be from a scientific journal. Okay. Another good source that you can consider is textbooks. Okay. And so you can use the textbook, one of the textbooks that we have for the class, or I can suggest, some textbooks for you as well. Okay. I have some in PDF form that I can give you as well for this project. And so, if you're having trouble finding sources, then let me know, and I can help you with that. All right. Any questions on this so far? Okay. All right, deliverables. And so there are 2 things you're going to turn in, submit for this project. Okay? So one is going to be a presentation. And so the presentation is going to take place all during the last week of class. And so, I'm going to give basically each group a chance to present in the final week. And the presentation will be anywhere between 12 and 15 minutes, depending on how many groups that we have. And so the presentation should basically summarize all the aspects of your project, and so it should go through the introduction, the biomechanical analysis, and the discussion. Okay, and so it should be kind of a nice package deal like that. And you should think of your final presentation as kind of like a lesson that you give. Okay, and so aim for your presentation to be as educational as possible. And then besides the final presentation, we have the final report. And so the final report is, has all the requirements that we talked about, before, but it's going to have a lot more detail than your final presentation. Okay. And that's going to be due on Monday, December 20th at 11:59 p.m. Okay. So that's the Monday after finals week. And again, I can't push that back anymore. Otherwise, I'm not going to have Christmas this year. Okay. And so the final report components, and so I know this is a little bit bare bones right now, but later on in the semester, I'll give you guys a template about what I expect more for each section, but this is kind of the idea. Okay. I don't have a length requirement, I never do for these projects. And so you can go over these amount of pages or you can go under, of course, it depends on how much content that you have. I'm not going to grade you specifically on the number of pages, but if you want a rough idea about, about the rough ballpark of where you should be, including all the figures that I expect you guys to put into the report, I expect it to be around 15, 20 pages. And so, that's a fairly conservative estimate. I expect, probably a lot of people will go over 20 pages, depending on how detailed you are. But, that's the rough ballpark. But again, I'm not going to penalize you on whether you go over or under this length. It's just a rough ballpark just to give you an idea. All right. All right, teams. And so, like I mentioned before, you can work in groups with up to 3 students. And so that's the absolute max. But you can also do this by yourself as well. And so, I'm going to be very flexible because, I know a lot of, or what you end up choosing is going to be based on, what the topic is. And so I don't want to limit you to, a specific number of students so that you end up working on something that you're not interested in. So, my goal is for everyone to work on something that at least is in their top 3 of, what they're really interested in looking into. Okay. And so, I think with this flexibility, I think it'll make it a bit easier to do. Okay. And so, if you want to work in a group, or if you want to see if someone else is going to take a particular topic, then, I would encourage you to use the Discord. Okay. And so that's exactly what the Discord is meant for. And so, if you're thinking about working on a particular topic and you want to see if someone else is interested in teaming up with you, put a message out in the Discord and say that, hey, my name is this, I'm thinking about doing this topic for the final project. Does anyone want to work with me? And then, then you can organize a group from there. Okay. Because the requirements of the project are not going to change, depending on how many group members that you have. And so, if you work together with more people, then I think it helps to spread the work around a little bit better. Okay. But of course, if you want to go by yourself, then that's totally fine too. Okay. All right. Any questions before we go over the topics? Okay. All right. So let's go over the list of topics that are available, just so that you can get an idea. And so I'll go over each one, very briefly for now, and then you can of course read them in more detail later. Okay. All right. So the first topic available is called gait analysis, right? And so gait, spelled G-A-I-T, refers to the manner in which a person walks, okay? And so, how a person walks, that's basically referred to as the gait. And there's a lot of really interesting biomechanics associated with this, because it's actually, it's something that we take for granted because it's something that we do all the time just to get from point A to point B. But there's a lot of interesting, muscle action, there's a lot of nervous system action, a lot of weight bearing action that gets happened during gait. Okay. And actually, one thing that gets measured a lot is, people's walking motion. And so, biomechanics or biomechanics researchers or shoe salesmen even, they're really interested in seeing how people walk so they can design certain devices for them. Okay. And so there's a whole field about this, about, people taking videos of people walking and then, seeing if you have some kind of walking disorder and things like that. Okay. And so this is a really rich topic area that, you know, I'm hoping someone picks because it's really interesting and there's a lot of literature out there as well. Okay. And so if you choose this topic, you know, I want you to, you know, kind of go from scratch about, you know, what is gait actually is, you know, what are people looking for when they watch your gait, and how does that affect, you know, certain types of either shoes that you wear, or, you know, what kinds of pathologies that you can have, and all those things. All right, so topic 2 is sports performance, okay? And so this is a topic where we can have multiple groups. Okay? And so if you choose this topic, I want you to choose a specific sport and analyze the biomechanics of all of the main actions that an athlete is supposed to do, okay? And so let's say that you choose something like basketball, right? And so a basketball player, you know, they're expected to do a certain amount of actions as part of their sport, right? And so, you know, you can think of just shooting a basketball, you can think of, you know, going up for a block, you can think of going up for a rebound, you know, getting into a defensive stance, right? Sliding back and forth. And so, you know, if for this topic, you know, I want you to, you know, take a look at each of those actions and basically perform a biomechanical analysis of each one and talk about, you know, what are kind of the more optimal things that you can do to optimize your performance in these actions. Right? And so let's say if you want to optimize your jump height, so how should you jump if you want to do that, okay? And so additionally, what I want you to discuss is, you know, considering all of these actions that these players are expected to do, what are some common injuries experienced by these athletes that, you know, that are maybe predisposed by some of the actions that they do, okay? And so there can be multiple groups that work on this. And so, you know, granted that everyone chooses a different sport, okay? And so I think there's a lot of potential for this topic as well, okay? All right, topic 3 is animal locomotion. And so this is another topic where we can have multiple groups. Okay, and so in this topic, I want you to choose a particular class of animals, right? And so maybe you choose felines, maybe you choose dogs. You know, I say here that I want to restrict this to just animals that walk on land, because, you know, that's very similar to how humans move, and we've been focusing on humans. But if you want to do like a bird or a fish, then I'm open to that as well. But, you know, just make sure you run it by me first and kind of, you know, and just so that we can talk about it. Okay. And so I think what's interesting about this topic is that the anatomy of your animal is going to be very different from human. And so I want you to go through a detailed description of, you know, what are all the bones and the main bones and the main muscles for this for these animals. Okay. You can just leave it off. It's fine. And, you know, and tie that into your analysis as well, right? And so when you go do like static analysis or dynamic analysis on your animal, you know, explain how the anatomy of that animal, you know, helps them perform these actions well. Okay. Yeah.
So like, I was thinking about this one. I thought it would be interesting because, like, you know, obviously humans are one of the only animals that walk on 2 legs.
Yep. Mm-hmm.
Birds.
Yep.
So can we analyze, like, did you say how many? We had to have 5 examples, right?
Yep. Mm-hmm.
So like, but what if we were to choose like a cat, a primate, like an orangutan or a chimpanzee that's like halfway between bipedal and an ostrich that does walk on 2 legs, but like its knees are backwards relative to ours. And then we can do humans because we're also animals. And then, you know, choose another one or whatever. And then compare how the biomechanics change when you go from like strictly quadrupedal to bipedal, to strictly bipedal.
Yeah, I think that'd be interesting. And so I think from that perspective, if you choose like a specific action like walking or running and do it across, you know, 5 different species, I think that'd be another way that you can take this analysis too.
Okay, cool. Because I just wanted to make sure we weren't locked into like one subgroup of animals.
Yeah, that's originally how I had it planned. And so originally I thought, you know, you would choose one animal and do maybe 5 different actions. But if you want to do like a cross species comparison of, you know, how different species walk, I think that'd be really interesting as well.
Okay.
Yeah. All right. And so, you know, multiple groups in this one, you know, and, you know, different multiple animals and just multiple ways to approach it. So, you know, as with anything, you know, if you're unsure, just, you know, just run it by me. And, you know, I think most times I'll say yes, you know, or I'll give you some feedback on how you can make it more interesting. Okay. All right. Number four is surgical reconstructions. Okay. And so in this topic, you know, I want you to look at the science behind, you know, what happens when someone has a catastrophic injury to their bones or the ligaments or their tendons. Okay. And so, you know, let's say that you completely rupture a tendon, or you rupture a ligament, right? there's a whole, field of science that goes into, how can you put a replacement ligament in there or replacement tendon, okay? And so they can even be minor things too, like, you hear about athletes getting plates and screws into their bones all the time, okay? And so for this topic, what I want you to do is I want to explore all the different types of surgical reconstructions that there are available. And I want you to do some analysis of, how does, after the reconstruction, how does this affect the athletes or how does this affect the person's ability to move relative to before their surgery, okay? All right, number 5. So number 5 is prosthesis design and manufacturing. So I expect, this might be a popular one because I heard a lot of people are interested in this from the beginning of the class, okay? And so prostheses are basic artificial body parts that are used to replace, parts on a person's body that, may be missing or not functional, okay? And, I think this is a really interesting topic just because in recent years, there's been a lot of really rapid advancement in this technology, especially in the fields of, 3D printing. And so I think 3D printing is becoming a new avenue for producing prostheses. And also in terms of control too. And so, how people control these prostheses and how, what degree of control is needed. I think there's a lot of really interesting topics for this one as well, okay? This one's going to be a little bit tricky because I do plan on talking about this on the week after we come back from Thanksgiving. And so, I am planning on covering this a little bit in the class just because I know a lot of people were interested in this. But I want you to go, obviously I want you to go a lot deeper than what I cover in the class. Okay. But I think it's such a rich area and there's so much kind of new technology with prosthesis. I think there's going to be more than enough content for you to kind of, develop this idea a lot more. Okay. All right, number 6. So number 6 is kind of a general topic of just any kind of device that's used to either assist a person with mobility or to enhance certain tasks. Okay. And so, of course, one thing that comes to mind for this is like exoskeletons, which is one of the topics for homework 5. Okay. And so, similar to locomotion, animal locomotion for this topic. At least what I had in mind was you would kind of focus on a particular class of devices. And so maybe you would focus on wheelchairs, maybe you would focus on, exoskeletons, okay? And then I want you to perform your biomechanical analysis on this, okay? In addition, and so since this one is a little bit unique because, within a certain class of devices, there's, because we live in a capitalist society, there's often going to be a lot of different options for you to choose, okay? I want you to perform a little bit of market research, as well into at least 4 different devices in this class. And I want you to rate basically the pros and cons of these devices, okay? And so when you're doing the biomechanical analysis on this topic, I want you to think about, which muscles or parts of the body are most impacted by this, okay? Or which parts of the body that the device is aiming to support. And then compare that to, of course, what happens if this person doesn't have that device, okay? And so, this is a very wide topic area too. And so, we can have multiple groups here, for a variety of reasons, okay? All right, number 7. So number 7 is the biomechanics of weightlifting exercises, okay? And so weightlifting or resistance-based exercises are a very popular way for people to stay in shape, okay? But I think it lends extremely well to kind of, the types of analysis that we do in this class. Okay? And in fact, we've been doing a lot of our analysis on weightlifting already. Okay. And so with this topic, I want you to really go deep and perform biomechanical analysis on several weightlifting exercises. Okay. And so for each exercise, I want you to really discuss about, what the proper technique is for this and why it's important. Okay. Because, like we discussed actually just last class, right? So proper technique is important, not only for making sure you get the most out of the exercise, but also making sure you minimize the risk of injury, okay? Okay. And so in addition to all that biomechanical analysis, I want you to dive deep into kind of the muscle and the tissue mechanics of this as well, okay? And so I want you to have a really detailed description of, what is actually happening underneath, what happens when you lift weights, and how that actually goes into building your muscle, okay? And so 7, I think this is a little bit unique because, in terms of the biomechanical analysis, it'll be very similar to what we've been doing in the class, but I want you to do a lot more research into kind of the cellular and the tissue mechanics that I think the other topics won't have nearly as much of, okay? Question?
something like this, and it also relates to some of the other topics too. Are we gonna be doing any type of dynamic analysis?
Yep.
Anytime, okay.
Yep, that's the next few weeks are going to be dynamics.
Okay, yeah, because like with a lot of weightlifting exercises like squatting and deadlifting, bench pressing, just all that stuff, and walking too and stuff. There's a lot of like the load is like very dynamic. You know, some people live fast, some people live slow. So
Oh yeah, yeah,
and I'm sure that would play a significant role in force development. So.
absolutely. Yeah, yeah. So the next portion of the class is dynamic. So we're definitely going to cover that. All right. And so the last topic I could come up with was robotics. Okay. And so robotics, you know, I think everyone here knows what robotics is, but but at least in terms of, you know, what we're interested in this class is, you know, we're interested in robotics that can either mimic or outperform human action. Okay. And so robotics as a field is extremely rich. And so there's lots of many subdisciplines. But out of those, I want you to mostly focus on robotics and locomotion, robotics design, and robotics control. Okay. And so since these are the ones that are kind of most relevant to human locomotion. Okay. And so for this, you know, I want you to think about or do your research into how robots can actually mimic human action. Okay. And in particular, you know, I'm particularly interested in seeing, you know, how do scientists design the actuators and how do they design the motors on these robots to mimic, you know, complex human motion. Okay. Because we've talked about, you know, that you have so many muscles in your body, and that's part of the reason why we can do all these like really complex and fluid motions. But on a robot, you know, when you put an actuator on there, you're very limited in terms of space of what you can actually put. Okay. And so how these scientists or how these robotics designers actually put these actuators on and actually use them to mimic, you know, real life human movement, you know, while keeping in mind that, you know, a robot is going to have very different mass properties than a human. You know, I want you to kind of really dive deep into that. Okay. And so another thing you can look into is some of the basics of control systems, because I think that's a really rich topic area as well. Okay. And so how the different actuators and how the motors basically all work together within a robot and how they're controlled, I think is a really interesting topic that you can dive into as well. Okay. All right, so those are all the ones that I could come up with, you know, at least over the last few weeks. But if you have something else that you want to study, maybe it's a fusion of a few of these different topics. You know, I'm fine with that. And so, you know, if you're thinking about something unique that doesn't fit into one of these categories, which is either maybe it's something completely different or maybe it's a fusion, then just talk to me, you know, and then we can kind of form the idea for that project together. Okay. And so, you know, again, you know, I want this project to be something that, you know, you have, I think a lot of people came into this class with an idea of, you know, I'm really interested in studying this aspect of biomechanics, or this is what I was looking forward to learning. And so, you know, I want to give you guys a chance to learn that and really research into it. And so, you know, if there's something you really want to do, just run it by me. And then, you know, we can formulate it into a project topic. Okay. All right. Any final questions on this before we jump into the lecture?
For topic number 2, like, can MMA be considered one of the sports for those?
Sure, absolutely. Yeah, I think so. Yeah, MMA would be really interesting because there's a lot of impact in that, and obviously injury risk is a lot higher. So yeah, I think that'd be a great one. Yeah. Lots of different styles in MMA too. So I think that'd be really interesting to see all the different styles. Yeah. All right, so start thinking about your topics. You know, get other people together if you want. You know, and then over the next couple of weeks, I'll put out rubrics. I'll put out templates for you, so that you can kind of start organizing the ideas. But I at least wanted to put this out to you guys so you can start looking for your sources, because, you know, 10 is kind of a lot of sources, like I know. But, you know, I think now is the kind of time to start doing that research and getting your sources together and getting information. You know, so you can work on this project throughout the next 6 weeks, which is what we have for this semester. Okay. All right, and so let me go ahead and stop this. I'm going to share my iPad. Okay. All right. And so we're going to dive into our next set of lecture notes now, which is linear dynamics, basically. Okay. And so a lot of this, a lot of this lecture notes is going to be fairly review. And so we're going to be going over things like center of mass, velocity, acceleration, right? And so, a lot of these things we've learned before, but I've tried to put in as many examples as I could of, of actually applying this to human motion. Okay. All right, so let's go ahead and get started because we are 30 minutes into the lecture. Okay. And so this topic is linear motion or linear dynamics. Of human motion. All right. And so, for the last few weeks, we've been doing static analysis, right? And so we've been going over all the different parts of the body, and the upper extremity, the lower extremity, the spine, right? And so we did kind of a combination of both, anatomy and also kind of static analysis at the same time, okay? And so this is fine, right? And so static analysis makes up a big part of our lives. But, as humans, we naturally move around a lot, okay? And so there's, a discussion of human biomechanics would be incomplete if we didn't factor motion into it, okay? And so this is kind of the first step. And so mathematically, actually not a lot is going to change. And so mathematically, we're still going to be doing force balances, okay, or force summations, okay. The only difference now is that instead of setting this equal to 0, the main difference now is that we're going to set it equal to mass times acceleration, okay. Where just like before, the forces that we're considering here, they're mostly going to come from either internally within the body, or they can come from some kind of external source as well. Okay. Right. And so in general, what you'll see is that, because we're considering motion and we have, this acceleration term here, the forces that we're going to compute in dynamic cases are going to be higher than they are in static, okay? Okay. Because now these forces are going to need to start to accelerate, right? And so they need to accelerate either the whole body, or they're going to need to accelerate different parts of the body. Okay. All right, and so I will say that this part of linear dynamics, it's only part 1 of the kind of the entire dynamics unit that we're going to be looking at. Okay, and a lot of what we cover, probably you should be able to do a lot of this analysis already. Okay, because actually, the main interesting dynamical behavior that the body does is actually rotational, right? And so when you think about moving your limbs around, okay. This is rotational motion, right? And so when you move your arm up, your whole entire arm is rotating about your shoulder, okay? And so the big part of the dynamics portion of this dynamics unit is actually going to be the unit after this, where we do rotational motion. But kind of before we start to introduce rotational dynamics, we have to review a lot of linear dynamics as well, okay? And so throughout this lecture that, we'll start today, probably finish up on Monday, you'll see how do you start to incorporate kind of really basic linear motion into your biomechanical analysis. Okay. Okay. Any questions on this so far? Okay. All right. So before we start talking about kinematics again, we have to review the concept of center of mass. So center of mass is a really useful and convenient concept when doing linear dynamics. And so basically the idea behind center of mass is that instead of considering the mass of a person or the mass of an object which takes up some volume, we instead kind of concentrate that mass into a single particle. Okay. And so let's say that we have a person, okay? And so this person has mass m, okay? And so in linear dynamics, since most of the time we're considering the motion of a person or an object in total, okay? A lot of times it's convenient to, instead of considering this entire person, we consider it instead as just a point mass. A single point with the same mass. Okay. And it's a lot easier to analyze linear dynamics on a point mass versus an entire body. Okay. And so let's very quickly review, how do you actually compute center of mass for an object? Okay. Okay. And so before we get into those calculations, let's go ahead and define or give a definition for what center of mass is. Okay. And so the center of mass is a unique location in space Okay. It's a unique location in space where the weighted relative positions of all of the mass segments sum to 0. Okay. And so basically the idea with center of mass is if I kind of draw the body kind of behind this, okay? If we consider, the mass of each of these segments individually, so we have the mass of the head, right? The mass of the 2 arms, okay? The mass of the legs, and maybe the mass of the torso, okay? And so if we sum the positions of all of these, okay, and divide it by 0, or divide by the total mass, then that's what we get for this center of mass, okay? All right, and so this definition I think is useful for the human body because a lot of times for the human body we consider each of the segments separate from the other ones, right? And so we consider the arms a separate segment from the legs, which is separate from the torso, which is separate from the head, okay? And so the way that center of mass is usually computed is we take kind of each segment individually, and then we, perform a weighted sum to get that center of mass. Okay. All right, any questions on this? All right. And so the center of mass, let me go ahead and write the formula, okay? Okay, and so I'm going to denote the location of the center of mass as RCOM, okay? This is going to be equal to the summation of R of MI divided by RI, or times RI, divided by the total mass in the system, okay? Where I starts at 1 and goes up to N, okay? And so I think the key to this whole operation is what the, what that quantity in the summation is, okay? And so what this is this is the product of the mass and position of each separate segment in the object. Okay. And so in this next example, we'll do an example to say to compute, where the center of mass is for a typical person in terms of the ground, right? And so if someone's just kind of standing normally, how high off the ground is their center of mass? Okay. And so what we're going to do is we're going to consider each of the segments of the body separately. Okay. We're going to multiply both the mass of that segment and the position of that segment. And then, sum them all up together, divide by the total mass, and that's going to be our center of mass location. Okay. All right. And so as an example, let's find the center of mass of this person's body. Okay. So let's say that we have kind of a normal person, or I guess in this case, a normal stick figure, okay? And we're going to consider the mass of 6 different segments on the person's body, okay? So let me go ahead and write a table. Okay. And so we're going to consider the mass of the head, the left arm, the right arm, the torso, left leg, and the right leg. Okay. All right, we'll list out, how high off the ground these segments are, okay? And we're also going to list out their mass, okay? And so the head for this person is going to be 1.78 meters off the ground, okay? The head is going to have a mass of 5 kilograms, okay? We're going to assume that this person is just standing kind of with their arms to the side, and so both the left arm and the right arm are going to have the same height, okay? And so the left arm is going to be 1.31 meters off the ground. And the right arm is going to be 1.31 meters off the ground. Okay.
Professor?
And we'll assume that the each arm has the same mass. Okay. Which is pretty reasonable most of the time. All right, so next we have the torso. And so we're going to assume that the center of mass for the torso is 1.37 meters off the ground. Okay, so slightly higher than the arms. And the torso is going to have a mass of 46.7 kilograms. Okay. Oh, is someone call my name? Oh. Our question, so how is the arm higher than the head? Oh, the head is 1.78, sorry. Yeah, the head is the highest. Yeah. Sorry, the volume on the in the class for the Zoom on the lecture, I had it pretty low. Yep. So did someone on the Zoom call have a question? Like Carlos? Okay. All right, so left leg. So left leg is going to be 0.6 meters. Oh, all right, question. So does it matter where the arm height is measured at? So we're for this example, we're going to assume the arms are to the side. But after this, we're going to do an example where the arms are going to be raised up, and we're going to see how that affects actually the center of mass. Ah, yeah. So it's going to be measured at the elbow. Yep. Right. So for each of the legs, yeah. So for each of the legs, we're going to assume that their masses are 0.6 meters off the ground. Okay. And each of their masses are going to be 14.9 kilograms. All right. And so with this data in mind, we can go ahead and compute the center of mass. Yes, yeah, and the legs, we're going to assume that they're measured from the knee. Yeah. Yeah, so for each of these segments, you can assume that they're measured at the middle of whatever segment that they're at. Okay, and so let's go ahead and start computing things for this formula. Okay. So first thing we can do is we can compute the total mass, right? And so the total mass is easy. We can just sum up all the masses here. Okay. Okay. And so total mass will be the sum of all the masses in the system. And so we have 5 kilograms plus 5.65 kilograms plus 5.65 plus 46.7 plus 14.9 plus 14.9. Okay. And we add all these together, we get 92.8 kilograms. Okay. All right. And so now that we have the total mass, we can go ahead and plug that in to our formula, right? And so HCOM. Okay. So I'm using H here just because we're only looking at the height from the ground. Okay. And so HCOM is going to be, first thing we're going to do is we're going to take the product of the mass of each segment multiplied by its position. Okay. And so starting with the head, we saw that the head was 1.8 meters off the ground. And we're going to multiply this by the mass of the head, which is 5 kilograms. Okay. Then we're going to take the mass of the two arms. And so since the two arms are identical, I'm just going to add a 2 right here. Okay, so each arm is 1.31 meters off the ground. And the mass is going to be 5.65 kilograms. Okay. Then we're going to add the position and mass of the torso. And so the torso is 1.37 meters. And the mass of the torso is 46.7 kilograms. Okay. And then we have the two legs. Since the two legs are 0.6 meters off the ground. And the mass of each leg is 14.9. Okay. And so if we divide this by the total mass, then we can get the center of mass. And so we perform all those calculations. And we get that the height of the center of mass off the ground is going to be 1.1375 meters. Okay. Any questions on this? Yeah, so HCOM is the same as RCOM. So I use R for the general formula because this can be the position for anything. But for this example, we're specifically just worried about height. And so that's why I use H. Yeah, but H, R, X, you know, they're all kind of interchangeable. Yeah, it's just position. Mhm. All right, any questions on this example? Okay. All right, and so let me give you some trivia and some data, right? And so for an average person, the center of mass is approximately 57% of their total height. Okay, and so it's slightly above halfway up your body. And so this is for men. For women, the height of the center of mass is about 55% of their total height. Okay. Okay, and so these are just averages, and so you know everyone you know varies. There's anatomical variations between people, but you know on an average sense, this is kind of the numbers. Okay. All right. And so just like I mentioned, you know previously, the location of your center of mass will depend on the orientation of your body. Okay. And so you can actually change the location of your center of mass depending on what you're doing with your body. Okay. Okay. And so let's redo the last example, but let's consider a case where the person raises their arms. Okay. Okay. And so if this person raises their arms, you know, you can kind of see from me that, you know, my elbows are now kind of in line with my head. Okay. And so what we're going to assume is that when they raise their arms, the height of their arms matches the head as well. Okay. And so now basically we're going to redo the calculation. H arm is now going to be 1.78 meters. Okay. All right, and so if we redo the calculation, and so you know our total mass is the same because you know we're not adding any mass to our body. Okay. And so if we run through the calculations again, but with the height of the arms higher, what we get is HCOM. HCOM is now 1.195 meters. Okay. And this is, and you know, which looks very similar to the last case, but if you compare the value, this is a difference of 5.7 centimeters. Okay. Right, and so the center of mass is something that's dynamic, and so it's not something that's constant within your body, right? So depending on what the orientation of your body segments are, that's going to change, the position of your center of mass. Okay? And so this is going to be really important because, right before we leave for Thanksgiving, we're going to discuss the biomechanics of balance, right? And so how the body keeps balance. And so the location or the height of your center of mass, it has a lot to do, or it determines a lot with how you keep balance, okay? And so probably you've heard that, the lower you kind of keep your center of gravity, the more balance that you have, right? So the more you kind of bend over, the harder it is for someone to push you over and for you to lose balance, okay? And so, we'll revisit this, the center of mass idea once we get to balance, okay? All right, any questions on this? Okay, pretty straightforward, center of mass. Okay. All right, and so now let's review the ideas of displacement, velocity, and acceleration. All right. And so, these three quantities right here are kind of the three horsemen of kinematics, right? And so what these three have in common is that they're used to describe, how an object is moving linearly. Okay? Okay. All right, and so let me just give a quick definition for these three, okay? And we'll talk about how they're related. I think we have time to do one more example before we head out for today. All right. So displacement. And so usually the variable for displacement is usually given by some symbol like X or something, okay? And what this does is it measures how far something has traveled. Okay? Okay. And this is measured in terms with units of length. And so things like meters, things like inches, feet, those are all used to measure displacement. Right? Okay. And the symbol that I'll use to denote displacement is an X with an arrow over it, because displacement is a vector quantity. Okay. All right, velocity. So velocity, this measures how fast something is traveling. Okay. And we can compute the velocity by taking the derivative of the displacement. Okay. Okay. And so if we take the derivative with respect to time of the displacement, then this is going to give us our velocity. Okay. And so if you look at this equation right here, then another definition you can give for velocity is that it's the rate of change of displacement. Okay. And then finally, we have acceleration. And so acceleration measures the rate of change of velocity. Right? And so in other words, it's how quickly velocity is changing. Okay. And so acceleration, which we usually give by the symbol A, okay? This is defined as dv dt. Or if we plug in the definition for v, this is the double derivative of displacement. Okay. And so acceleration is going to be especially important for us because, like we showed at the beginning of class, right? We're going to be making a lot of relationships like this, okay? And so acceleration is important because we need that to relate to forces, okay? Because the sum of the forces on an object is equal to the mass of the object times the acceleration. Okay? And so we just finished talking about, center of mass. And so, we know how to compute, mass of an object and where it's located, okay? And now that we have an idea of what the acceleration is, we're now ready to do a kind of a pretty simple, fairly simple example. Okay? All right. Any questions on this? Okay. All right. So let's do a quick example before we close up for the week. All right, so let's do an example of someone of a person doing a pull-up. Okay. And so let's say that we have a bar up here. Okay. And so let's say that this person's arms are super long, okay, but his legs are really short. Okay. And so let's say that this person has a mass M. Okay. And in order to pull himself up, he basically needs to pull down on the bar so that the bar can give a reaction force, okay, that's going to pull the body up. Okay. And so we're going to assume that he's going to pull equally on both arms. And so he's going to apply a force F on the bar. Okay. Okay. All right. And so if we assume that this person has a mass of 75 kilograms, and at the very beginning of the pull-up motion, let's say that he's accelerating upwards at a rate of 4 meters per second squared. Okay. Okay. All right. And so with this in mind, let's compute the reaction forces at the bar that's needed to make this happen. All right. All right. And so, just like we always been doing in the static case, we're going to do a sum of the forces. Okay. And so if we consider the, the two upward forces on the bar as F, okay. Opposing F is going to be gravity, right? And so we have a downward force of M times G. Okay. And so the sum of the forces in the Y direction, we're going to have 2F, because we have one F on each hand. Okay. We're going to subtract mg because mg is going in the bottom direction. Okay. Okay. And this is all going to be equal to ma. Okay. All right. And so we know m in this case. So m is 75 kilograms. We know a is the upward acceleration, which is 4. Okay. And we know gravity, which is 9.8. Okay. And so we can easily solve this equation for F. Okay. And so we say that F is equal to m times a plus g divided by 2. Okay. Okay. And we get very simply that the upward force has to be 517.5 newtons. Okay. It should be 75. Yeah. Sorry, my stylus is getting kind of scuffed. Yeah. 75 kilograms. Mm-hmm. Right. So let's compare this force. Let's compare this force to the static case, right? And so in the static case, A is equal to 0, right? And so if A is equal to 0, then we get a force of 367.5 newtons. And so obviously, the force has to be much higher in the dynamic case because that's the force that's going to actually pull them up, right? And so if you compare this, if you try this yourself, and so you go to a pull-up bar and you just hang there, right? And so just hanging there, you only have to exert a certain amount of force. But if you want to start pulling yourself up, that's going to take, more work, more force. Okay. All right, any questions on this example? No, pretty straightforward, right? Okay. All right, and so that's, this is kind of like physics 101 again, right? And so nothing too bad. And so now let's actually take this and see how we can apply biomechanics to this, right? And so these two forces here are this 517 and this 367. These represent external forces that are being placed on the body, right? And so basically this person's weight has to be supported. And so depending on if the weight is accelerating upwards or if it's staying still, some external forces have to be applied on the body to raise this up, okay? And so what we can do from here is that we can take these forces and apply it onto each individual arm to see, how much muscle force is being exerted by the, well, in this case, we're going to consider the back muscles, okay? Okay. All right. And so, I want to make a quick caveat before we actually dive into this. And so, what we're going to be performing is basically pseudostatic analysis. Okay. And so we're going to be, performing our, force and moment balances as if it were static. Okay. Because we haven't yet gotten to rotational motion yet, okay? And so if we truly wanted to treat this the arm as a dynamic system, we have to kind of understand rotational dynamics, but we're just not there yet, okay? And so we're basically going to consider this as pseudostatic, okay? And so in reality, the forces that we're going to compute in the muscles are going to be higher than what we're going to be computing here. because we're kind of neglecting the motion of the arms itself. Okay. But at the very least, from linear dynamics, we have a sense of how much more external force is being applied onto the arm. Okay. And so we will see a difference between the dynamic case, the dynamic force and the static force. It's just not going to count for everything because, in reality, the arm is going to be rotating a lot as you perform the float motion. We're just not going to be able to consider that. But, once we get through rotational motion, then, you'll be able to actually characterize those things. Okay. And so if you want to kind of justify the pseudostatic analysis, you can think of this as performing the analysis right when the person starts to accelerate upwards, right? And so you can imagine that they're hanging there and then, they're going to exert their muscle. And then in that brief moment when, their body is kind of stationary right before they start moving, that's the case that we're going to consider. Okay. All right. And so we are just about out of time, but let me go ahead and draw the figure for you. Okay. Okay. And so I'm gonna perform the analysis on just one of the arms. Okay. And so let's say that this is the person's elbow joint, and this is their arm. Okay. And from the previous solution, okay. Right. So we can say he's grabbing onto the bar right here. Okay. There's going to be an external upward force of F right here. Okay. Where that F, at least in the dynamic case, this is 517.5 newtons. Okay. Opposing this force is going to be a muscle force, right? Okay. And so in this case, we're going to consider a force from the back muscle. Okay. And so that's one of your oblique muscles here. Okay. And so it's the muscle kind of on your side, and that's going to be responsible for kind of pulling your entire arm downwards. Okay. And so if we analyze this with respect to the shoulder joint, okay, we can do basically just as we did before, computing muscle forces and joint reaction forces. Okay. It's just that now our external force is a little bit higher because we're considering motion. So we did that already. And so we divided by 2 on this page. Yeah. Yeah. And so we're only going to do the analysis on one arm because the other arm is going to look exactly the same in theory. Okay. All right. Any final questions on this? And so I hate to leave it in the middle of an example like this, but we'll pick this up on Monday. Okay, all right, so that's all we got time for. So thank you everyone for tuning in. I'll send an email with all the project information that we discussed today, just so that you have it in writing. And so, the main thing I want you to think about this weekend is, what topic that you want to do for your project. Go ahead and form your groups. And then, once you settle on a topic, go ahead and run it by me, just so that I can reserve it, just to make sure no one else does it. And then you can start your research. Okay. All right, so thank you everyone for tuning in. Hope you guys enjoy the rest of your afternoon, and I will see you guys next week. Thanks, guys. You guys. Yeah.
I have a question about the weightlifting one.
Mhm.
I've never done dynamics in 3 dimensions before.
Mhm.
I've only taken three, whatever it is. So, and I feel like some stuff is a little bit like the deadlift, yeah, you could definitely model that 2 dimensions for sure.
Mhm.
But I feel like bench press, well,